In October 2026, the European Space Agency will release the first major dataset from the Euclid Space Telescope. The release will deliver high-precision cosmological data through two primary channels: spectroscopic baryon acoustic oscillations, tracking galaxy distributions between redshifts of 0.9 and 1.8, and photometric weak lensing, observing how mass distorts light across deep space. For decades, standard theoretical cosmology has relied on highly flexible models. When observational data contradicts the expected expansion rate or early galaxy formation, the standard practice is to introduce new parameters, retroactively tuning the equations to absorb the anomaly. A competing framework, mode identity theory, rejects post hoc fitting. It has locked its exact observational expectations years before the Euclid data arrives down on Earth. We have mapped these predictions into a rigid, mutually exclusive falsification matrix. It pits the challenger against 4 standard models across 5 specific observables. By publicly pre-registering these explicit thresholds, mode identity theory forces a 0 degrees of freedom test. It either survives the incoming data entirely, or it is permanently falsified. To understand why these predictions diverge so sharply from standard models, we have to look at the foundational geometry. Standard cosmology relies on the FLWRW metric, assuming an expanding spacetime. Mode identity theory discards expansion entirely. It postulates the universe is a finite, static three-sphere with an embedded Möbius boundary. Traversing this one-sided surface forces a mathematical sign flip on any field, creating anti-periodic boundary conditions and generating a standing wave with a 4π period. In this static geometry, space does not stretch. The measurement that standard physics interprets as cosmic expansion is simply phase advance along the temporal edge of this standing wave. This forces a complete reinterpretation of the cosmological constant, lambda. It is no longer a fluid vacuum energy driving expansion. It is a rigidly fixed topological ground eigenvalue determined by the radius of the three-sphere. Because this topology is rigid, it mathematically dictates 5 distinct observational signatures that a flexible, expanding universe cannot naturally replicate. Replacing parametrized expansion with a rigid static manifold produces a cascade of exact predictions, and Euclid is uniquely positioned to test them. The first test on the scoreboard dictates the stability of the cosmological constant over time. Standard parametrized models allow the density of dark energy to evolve. Recent fits from the DESI survey suggest exactly that, a time-varying dark energy density at different cosmic epochs. This compares standard models against mode identity theory. Because the challenger defines lambda as a topological eigenvalue, dark energy density cannot evolve. It traces a perfectly flat line across all redshifts. Euclid will map this using 4 precise redshift bins between 0.9 and 1.8. The falsification rule is absolute. If a model-independent reconstruction detects any variation across these redshift bins at a 2 sigma confidence level, the theory dies. Conversely, if Euclid proves lambda remains entirely static, the complex, time-varying parameterizations currently favored in cosmology lose their empirical justification. Row 2 shifts the focus from dark energy to the fundamental acceleration scale, known as A0. Standard cosmology operates without an acceleration scale, relying instead on dark matter halos to explain galactic rotation. MOND, the primary modified gravity alternative, posits that A0 exists but is a strict universal constant. This graph charts the predicted evolution of the acceleration scale. While MOND requires a static baseline, mode identity theory dictates its scales proportionally with the Hubble parameter over time. Quantitatively, at redshift 2, the scale must be 3 times higher than its local value today. Euclid will test this scaling enhancement using galaxy-galaxy weak lensing and the stellar mass-halo mass relation. Confirming a redshift-dependent acceleration scale would simultaneously dismantle the dark matter framework of standard cosmology and the constant gravity assumption of MOND. Row 3 addresses the trajectory of the dark energy equation of state. When standard 2-parameter models analyze recent cosmic data, they report a phantom crossing, a point where the dark energy value dips below -1. Mode identity theory mathematically forbids a physical crossing. It insists the underlying value is always strictly greater than -1. This visualization demonstrates how a false crossing occurs. The theory claims any observed dip is a template projection artifact. Forcing geometric data from a static topology into expanding universe equations distorts the curve, falsely forcing the output below -1. To falsify the challenger, Euclid data must prove through a rigorous fiducial split that the phantom crossing is a physical reality, not a mathematical distortion. If the crossing is an artifact, then current theoretical models are expending resources trying to explain phantom dynamics that never existed in the first place. Row 4 targets the abundance of massive galaxies at extreme high redshifts, beyond c = 10. This test is anchored to the immediate tension created by the James Webb Space Telescope. JWST has identified early galaxies that are too massive, appearing too quickly for standard models to easily construct. Proponents of standard cosmology argue these massive galaxies are anomalous, expecting the tension to resolve as larger sample sizes correct the statistics. Mode identity theory predicts the exact opposite. It expects Euclid's vast wide-area photometric survey to prove this high abundance is the actual cosmic baseline. This connects directly back to row 2. The exact mechanism that allows these massive galaxies to form so quickly is the enhanced scaling acceleration value operating in the early universe. Euclid will convert a narrow field of view into undeniable statistical volume, forcing the physics community to choose between standard dark matter halos and modified early dynamics. The final row looks for a highly specific anomaly in the expansion rate equation itself. Standard cosmological formulas account for radiation, matter, and curvature. They do not contain any isolated term that scales linearly with redshift. This mathematical breakdown isolates the expansion rate derived from the phase clock model. Mode identity theory explicitly demands this linear term, and it mandates that the coefficient attached to it must be strictly negative. The precision of Euclid DR1 is forecast at 1 to 2%. That may only be enough to yield a null result, deferring the final ruling on this specific coefficient to data release 2. But even a fractional detection of a negative linear coefficient in the initial data would establish an empirical presence that the foundational equations of an expanding universe simply cannot accommodate. We now have a completed matrix, 5 locked predictions derived from a static topology, arrayed against the expectations of standard cosmic expansion. These rows are adjudicated independently. A single miss against any designated threshold destroys mode identity theory. This deliberate vulnerability rejects the safety net of tuning variables to match unexpected telescope outputs. The theoretical debate pauses right here. The predictions are permanently sealed, and the raw observational truth takes over. When the Euclid data finally arrives, it will execute a strict binary outcome. It will either dismantle this topological framework or falsify the core expansion mechanism of standard cosmology. By stripping away post-hoc adjustments, this pre-registration removes human bias from the equation. The data alone will decide the architecture of the universe.